And the webinar of today is, the title is Climate Data for Engineers and Engineering. We will have two speakers, Trevor Murdock and Ryan Smith from the Canadian Centre for Climate Services. And during the webinar, you can interact with the computer or with your phone. You can interact with your computer in the website poolab.com/CCCS, or with your phone in the number, texting in the number 37607 and with the code CCCS. Thank you everyone for attending the webinar today, and I give the word to Cristy that will start with the agenda.
Thanks, Noise. Hello everyone. Good evening. I'm Cristy from Ottawa. I'm the organizer of today's seminar. I'm so excited to have you here tonight to learn, share, and discuss our climate change topic. I would like to start my introduction for the seminar by acknowledging that we are meeting on Aboriginal land that has been inhabited by Indigenous people from the beginning. I want to show my respect for their contributions and recognize the role of treaty making what is now Ontario. Thousands of years after first treaties were signed, they are still relevant today. We're grateful for the opportunity to meet here, and we thank all the generations of people who have taken care of this land for thousands of years. This seminar is organized under a group of people at the PEO who care about climate change issues and really want to make a difference based on our multidisciplinary background. Our mission is to help engineers, practitioners, academics, decision makers, and the regulatory committee members to set a vision and work on action plans, strategies for the climate change adaptation and mitigation in Ontario. This 90-minute seminar tonight will include the formal presentation with interactive exercise as well as time for questions and discussion. Topics to be covered include how historical and projected future climate data can be used by engineers for their engineering work in Canada. Following a brief overview of the scientific basis for the climate change and the latest projection for Canada from the most recent Intergovernmental Panel for Climate Change reports. The remainder of the presentation will focus on the availability and use of some of the most common climate parameters needed for planning, specification, design, operations, and maintenance of civil infrastructure and buildings, including indices of extremes. It will conclude with an overview of available national and regional sources of data and projections, their scientific basis, assumptions, limitations for engineering applications. Finally, I would like to express my appreciation for all co-sponsors who have been working hard together to make this event happen. Without your support and collaboration, we cannot go so far. Now, please welcome our co-sponsors, representatives, and members from PEO West Toronto Chapter, PEO East Toronto Chapter, PEO York Chapter, PEO Ottawa Chapter, PEO Willowdale Thornhill Chapter, Toastmasters Speaker Club of Ryerson Engineering, Toastmasters Toronto Engineering Club of Speakers. Now I would like to pass my torch to Afshin and Marcel to introduce our speakers. Thank you.
Thank you, Cristy. Hello, everyone. I'm welcoming Trevor Murdock, is the Manager of Data and Products at the Canadian Centre for Climate Services within Environment and Climate Change Canada, who has been a climate scientist who has been one since before it was cool, thanks to a master's degree in paleoclimate modeling from the University of Victoria in 1995. Trevor has focused on helping people do useful things with localized climate projection since the inception of the Pacific Climate Impacts Consortium in 2005 and at the Canadian Institute for Climate Studies before it. Thank you.
So I was trying to get this to work.
Hello, good evening, everyone. Tonight I have the honor of introducing Ryan Smith. Ryan Smith is a policy analyst with the Canadian Centre for Climate Services, a branch of Environment and Climate Change Canada. He received his Master of Science from the University of Manitoba in 2013, where he studied meteorology and climatology. He has taught courses in atmospheric sciences, human environmental interactions, and climate change. Ryan is a self-taught computer programmer and cartographer and has spent much of the past decade developing software that translates global climate model output into visually pleasing and intuitive maps of local climate change impacts. He has been invited to speak at several conferences and has several publications in the field of climate science, and it is our pleasure to have him speak tonight.
All right, thanks for the introductions. Are we diving right in? Was there something else? No? All right. I also just want to acknowledge with gratitude and respect the Lekwungen peoples on whose territory I live and work. So I'm coming from Victoria, BC. So that's the Songhees, the Esquimalt, and the Saanich peoples. Our Canadian Centre for Climate Services stretches across the country. Ryan's actually in Winnipeg. So we'll dive right into just give you a sense of what we're going to be covering tonight. From big picture kind of context, use this driving analogy. And because I'm from the West Coast, I would love it if anyone can say in the chat if there's somewhere in Ontario that has as straight of a road as between, there's nothing in BC, but between Calgary and Edmonton is the example I always use. So you can basically drive from Calgary to Edmonton looking in the rearview mirror. That's how straight the road is. And, we've been able to, engineers for centuries have been able to design for a roughly static climate. We've always had climate variability, but we've had a roughly static climate compared to the last century and where we're headed in the next century. And so the analogy here is that we're no longer able to drive looking backwards only. We need to start not looking in the rearview mirror, but looking future and using future projections. And the other bit to sort of pieces to this is that we're already in the wiggly part of the road. It's no longer straight. And then this last bit about the range of conditions being wider than ever. It's harder to drive in a wiggly road. Like if you were then to turn around and go from Calgary to where I am in Victoria, you're going to go over a bunch of mountain passes, and it's harder to navigate than the straight road. So hopefully this analogy will make sense by the end of the talk. The other little bit of context, some graphics there. We won't go into this at all. We're not engineers ourselves or lawyers, but just to recognize that we understand that all of this, how as an engineer to use climate information, is you're receiving this through the context of the duty to make use of data and knowledge and minimize risk and to ensure that you're not liable. So I think this would be a great topic for another presentation. I have some people to suggest. I know David Lapp, who suggested us, can speak to this, but there are some others as well. So we'll touch, just to say that we're aware of this kind of filter, and we might touch on it a little bit. It won't be the main thing. Okay, we're diving right into the first interactive exercise. I think a few people have answered already. And then after this, I'm going to pass the baton to Ryan. Some of us will be moving back. I will be swapping back and forth in different sections. These are some great answers already. So the question is, what are the most pressing issues or most common challenges facing your work today? This question is not on topic. Well, that's kind of what we're trying to get at. Is how does climate change fit in, or does it, to what you're concerned about? It's also just a way of getting you to test the full EV. So it's a bit of a warm up. Supply chain constraints. So if anyone is having trouble logging in, you can see up here at the top how to answer here. What we'll do is, just so that we don't get too far behind, because we do have a couple hundred people here potentially, or over 100 anyway. We will move on from this slide right now, but you keep answering until we get to a new question. Don't answer the old question when we get to a new question, but you can keep answering up until we ask a new question, and we'll include a result. All of the results will be included in the slides that we'll send at the end. All right, so, all right, climate change, maybe not the top here, but oh yeah, multiple and contradicting IDF groups. That's a great one. We'll touch on that and we'll get into it maybe in the longer questions. All right, I'm going to move to the next slide and hand off to you, Ryan. Again, you can keep answering that if you like.
I love the one about too many emails, you know, with questions that could be resolved just with a phone call. Isn't that? And there were some great responses there. Thanks. Okay, I am going to do a very, very quick, I promise you very quick, climate 101 section here, because I think we all need to be just on the same page about some basic definitions. And we'll start here with the difference between weather and climate. I know we all have an intuitive understanding of what the differences between weather and climate are, but sometimes our intuition can lead us astray. And we see that a lot. And I think it's really important to point those moments out. Weather, like this graphic shows here, it tells you what to wear on a given day. Climate, the analogy here is it's the type of clothes you need to have in your closet so that you're prepared for all different types of weather. So in this analogy, climate change, if climate change occurs and you don't adapt your closet, then potentially you have a situation where you don't have the correct clothing to wear outside, and you are potentially at risk of some environmental exposure, like extreme cold or extreme heat. And it's the exact same thing when it comes to physical infrastructure. If we don't adapt our physical infrastructure to climate change, we risk exposure. And we're going to see, even if our structures are over-engineered, even if we take into account such a wide range of weather in our region here, extreme hot summers and extreme cold winters, climate change is still having such a profound impact that we could actually be looking at operating outside of our design considerations. So let's just go into this in a little bit more detail here. So we can look at the recent climate of Ontario. This is annual average temperature. And you can see there's lots of variability, wiggle in this from year to year. There's hot years, there's cold years. We can draw a trend across these data and discover that, hey, there is a warming trend, but there are certain years that stand well above or below average, like 1988, for example. 1988, I don't know, for folks who might remember, was a particularly warm year here in Ontario. And if we go to the map, you'll see that Ontario and much of the central US and Canada was experiencing drought conditions. So it was a very challenging year. But if you look at the global map, you can see there's just as many blue spots, which would be colder than average spots, than there are orange and red spots above average. And the global average temperature, which is circled in the top right, is pretty much at zero, which is to say average, 0.15 degrees Celsius above normal. But we can take another year as an example here. The winter of 2014-2015 was a particularly cold year, a very anomalously cold year. And look at this map. I find this fascinating. It's pretty much, if you look at the Northeast US and Ontario, it's one of the coldest, or I should say that the place that logged the coldest below normal temperatures for that year. Compare it to almost anywhere else on the planet. We had forest fires in Europe and Asia. There were lots of challenges with drought. And in the US Senate, they brought a snowball in for show and tell as an example of saying, hey, well, look, it is so cold outside. How can climate change possibly be happening? Remember what I said about our intuition leading us astray? This is a great example. Even though it's cold out, and I'm in Winnipeg, we just had one of the coldest, snowiest years ever. It was terrible. It's still, in the context of a global climate system, we're still looking at warming. And in this case, half a degree of warming by 2014, 2015. I'll show you one more example here. We've got the year 2018, which was a very warm year on record. I mean, at the time, it was the warmest year on record, but we've had a couple of those since. Ontario was basked in multiple heat warnings. And drought, again, was a huge consequential issue. And as you can see, as this map, as that global average temperature continues to warm, the map shows more and more of the reds and oranges and less of those blues. And so the chances of having a climate, a weather situation that's above normal is increasing drastically. All right, so I think we've got a poll EV question up next here, Trevor. And here it is. So what was remarkable in the last 3 years in your location in terms of extreme weather or unusual seasons? And what were the impacts? So give yourself a second to think about that. Type your responses in. We would love to hear from everyone. As Trevor said, it's a big group, but it's for us, we'll be able to look at these responses later too. So sure, or put them in the regular chat. Trevor, you think it's even working?
I'm not sure. We don't have any answers here. Let's see. Looks like this one didn't activate properly. Let's just, so if folks want to enter this one in the chat, hopefully this is the only one that's broken. But yeah, it hasn't updated on the site.
On poll EV, it hasn't advanced to the next question.
All right, well, that, if we have this for a lot of slides, I'll look into manually setting them, but let's hope this is the only one. Thanks everyone for switching to just commenting in the chat. So hot summers, we've got a microburst, forest fires exacerbating floods. So feel free to keep doing those. I think in the interest of time, especially since we don't have the live update, I will just move on to the next bit. But feel free to keep those impacts coming of what you've seen. And again, not everything that has occurred is due to climate change. You know, there's a whole area of research in attributing what, you know, for any given event, how much more likely was it because of climate change? But we're just interested in what are the kinds of extremes that you've been noticing in the last couple of years. Okay, so returning to this figure that Ryan showed about the year-to-year variability in Ontario for the past, how do we move from that towards the future? So kind of squish the past into the left-hand side. And it's tempting to sort of extrapolate that line out in the future, but the problem, there's a bunch of problems with that. One is that the climate system is not linear, so you know, what trend do you draw? Where do you start your trend line? And so what we need to do is actually take what we know about the physics and biology and chemistry and everything that interacts with the climate system and model that. And it sounds complicated. We use these big supercomputers that have 3D grids in the atmosphere and the ocean, but it really boils down to modeling the motion of fluids on a rotating sphere. The atmosphere is a fluid that's not very dense. The ocean is a fluid that's more dense. They exchange heat and momentum. And you know, as I said, there's other complications like you know, terrestrial systems and ice systems and things like that. But essentially, it comes down to fluid on a rotating sphere, and that's something we can model very well. And so we use these climate models to give us future projections. The first thing that we have to do when we want to model the future, and so what we're looking at is climate model projections for Ontario from an ensemble of these global climate models. And the first thing we have to do is make some assumptions about how much greenhouse gases we're going to emit as a society. That's the main driver of future climate change over the coming century. And so the difference between these three red lines, I'll put a table up here for those of you who are familiar with this jargon, but you don't really need to know about it. The main thing here is that these three scenarios that I'm showing here, and there are a few more scenarios as well, but these three sort of encapsulate the range of plausible futures. They're purposely chosen so that the red line here is a kind of a high emission scenario. There's some debate around, does there even exist enough coal and oil in the world to emit that much that fast? And there, similarly on the blue line there, there's some debate. This kind of involves getting to net zero carbon within a couple of years. and then continuing to kind of suck carbon out of the atmosphere, equivalent to how much we emit after that. So that's pretty ambitious. There's some debate as well around whether that's even possible. But again, these are meant to sort of encapsulate a range of possible futures. The climate goals that Canada has committed to are sort of in between this yellow and blue line. And okay, so a couple of takeaways from this. You all know about a bell curve and sort of fitting a, if you've ever had your grades fit to a bell curve. So if we flip this bell curve on its side and sort of use that to represent the, the extreme hot and extreme cold events of Ontario, this is annual average temperature averaged over a whole province. That's important to keep in mind. And we look at this bell curve of annual temperatures in the past. And we go all the way to the worst case scenario here, end of the century under the highest scenario here. We're looking at a future that's actually mind-bogglingly different from the past that it's hard to even wrap your head around it. It's hard for me to wrap my head around it, even though I've spoken to this many times. You're looking at climates that have not been observed for at least millions of years, if we were to get to that level. And one way you can think about how different that is, you can look at how the fact that by the end of the century, when you have, how Ryan was showing anomalously cold and anomalously warm year maps there, those years are usually associated with sort of big impacts on the landscape. The anomalously oddly cold year that would occur at the end of the century under this scenario is actually a year that's warmer than, if you sort of slide over to the left, warmer than the warmest of the warm years of the past. And so the average is warmer than that, and the warmer years are warmer than that. I keep in mind, we're doing a lot of averaging. So this is averaging over the whole province and averaging over the year. So it's not like there's no single day that would occur in that future is like inconsistent with a single day of weather that would have occurred in the past. But the averages completely different place is the way that we kind of tend to think of that. So we want to avoid that. And the good news is we're actually, for as little progress as there's been on reducing greenhouse gas emissions globally, we are actually doing better than that line so far. So that's a good thing. In terms of, designing for this no longer straight road, curvy road that we're driving down. For most infrastructure, most design, most of you will be facing probably only needing to look towards the middle of the century for most things. And some things do need to last at the end of the century, but mostly in adapting to climate change, the focus is around the 2050s. And when you look there, there's the sort of choice of scenario almost evaporates a little bit. The difference between this worst case scenario and a lower, more optimistic scenario is not too large. And if you, instead of going sort of vertically, kind of go over horizontally, this 2050s under this sort of overly pessimistic scenario, worse than we're doing right now, but being engineering conservative, the 2050s under that scenario is the 2070s under a middle scenario. So I'm sure you all have had things where you wish someone had designed an extra 20 years of lifespan into whatever people keep using buildings or using things longer than they were designed for. So that we can think of this uncertainty in time rather than in having to pick a scenario. But the last kind of major point on this to make, and then we'll go into another, hopefully go into another totally exercise, is that even though this, this whole range, it sort of brings up the U word, uncertainty. What do I deal with? There's a bunch of different numbers here. You need a single number. Which one do we pick? And so it's tempting to go back to the historical because at least there's only one number there. But we're intentionally picking a number that is incompatible with any of the conditions of the future. So we don't want to pick a number that we know will be wrong just because it's convenient, because it's a single number. And so up until recently, that things like building codes and standards, it has been recorded, yes, have only had historical data in them. As Ryan mentioned, we get to the resources, the most recent building code had some future projections kind of associated with it. And maybe by the next building code, we'll have guidance for how to explicitly take that into account. But we're living in this wonderful, wacky, weird world where we know the climate is changing, but we don't have super clear step-by-step guidance on how to do it. So speaking of dirty words, I'm going to ask you about the F word. I know this stereotype might not be that engineers love talking about their feelings, but after I show that graphic, I always like to ask people this. Oh, this is actually working. And this is important. One word, if you really want to put two words, you need to put a dash in between it or an underscore. And the reason I like to show this slide and ask people how you're feeling right now is because you kind of have to deal with the frustration, because your life's more complicated than it would be in a static climate, or the overwhelm. But also people are, I see some hopeful. There's some challenged, concern. So there's just some contradictory feelings in here. And I think it's actually really important to know that all of you are kind of experiencing this, it's just like COVID, which came out of nowhere. It's another sort of complication and source of uncertainty that we have to now deal with. And also a chance to process your worry and anxiety and stress. Sorry to stress you out. The good news is, maybe since a lot of you are feeling worried, I will say that even that worst case scenario, you see in the news, you'll see a lot of headlines that are often, even if you read the article itself, it's not consistent with the headline, but you'll hear headlines about, human extinction and stuff like that. Even that worst case scenario is far from, complete human extinction and all of that kind of stuff. We can keep ourselves onto those lower emission scenarios that we've committed to. We can avoid that stuff. We're only facing a bunch of hard stuff, but not actual complete doom. Yeah. So I think it's important to note that doom is not doomed is not actually one of the scenarios. It's important to note that because otherwise you might give up, and that's not actually consistent with the science. All right, I'm going to move on from this. You can keep entering your feelings into this, and I'm just going to summarize. We're going to repeat the slide a few times because it's basically the takeaway. It's kind of saying what it said on that first slide in a different way. What we're focusing on in this hour is that considering future climate change in engineering is necessary. That slide was motivating, necessary. Now we're going to start getting into possible. And eventually we're going to get into and you can do this right now. This information is available right now. I'm going to pass to Ryan here. Thanks, Trevor.
Yeah, I thought that was awesome. That was really cool. And just thanks to everyone again for participating with that. And I'm trying to read the chat. There are some questions coming up in the chat that I don't even have time to answer, but hopefully I'm going to try to paste them. We can get to them at the end. But thanks to everyone so far for their participation. Okay, so we have a lot of uncertainty, right? And we're feeling quite anxious about it. So what are we going to do about it? This is where kind of the rubber hits the road, and where we have to come up with some framework for understanding our impacts, our vulnerability, and our risk to climate change, so we can come up with some priority actions. So there are lots of different risk vulnerability frameworks out there. Certainly, we don't have time. There's a whole course in understanding all of these. Different sectors have different frameworks that they follow. For engineers, though, PIVC really stands out as PIVC standing for, I'm gonna look at my notes because I can never remember. It's Public Infrastructure Engineering Vulnerability Committee Protocol. So I think it's PIVCP is actually how it should be named. But anyways, PIVC, which is one of the sort of most intuitive, I find, ways of understanding your system and the components that make up an engineered system, understanding climate changes and how they impact those components and systems, and then scoring the consequence and the magnitude of those, the likelihood and the consequence of those vulnerabilities to come up with some sense of risk so that we can start building a priority list of actions. So at the heart of any a risk assessment process is something like a risk matrix like this, where risk is defined here as likelihood, how likely is an event to occur, times consequence, which is to say how bad would an event be if it did occur. Okay, and you will see some slightly different language here and then, but essentially, yeah, likelihood times consequence is the very basic definition of risk. We can throw a couple quick examples on here just to illustrate different types, different events and how they would score on this table. So take an asteroid impact. It's a hopefully very low likelihood event, something that maybe occurs every few million years. But the consequences, of course, are astronomical. And so it would score somewhere in the top left versus a mosquito, a non-West Nile carrying mosquito, which would have an extremely low I mean, you get itchy, that's your consequence, but occurs, thousands of times in a particular summer. Both of these events actually score the same in terms of risk, okay? And so that's kind of in the low to medium category. But take something like a pandemic, like COVID, which has a likelihood rating of somewhere in between these two events and a consequence rating that is quite high. We can get up into the upper right part of this risk quadrant, which is where we have high risk, and therefore that's going to be the type of events that we want to try to plan for, to engineer to our systems, to adapt our systems for those types of events. Okay, I guess it's important just to note very quickly that this risk matrix has a mirror image cousin that we typically do ignore, but it's still there. We can have good consequences, right? And so think about winning the lottery, right? That's a very low likelihood event, but has a very positive, although Trevor pointed out, it's not always so positive. Sometimes money ruins people, but a very positive outcome, which would put it down here in the risk matrix. Okay, so let's actually do a real example here. Okay, we can look at say, let's imagine, and we don't have to imagine because it actually did happen, that we're in charge of some transportation and sewer infrastructure in the city of Toronto, and there's a major rainfall event. In fact, there's a 1 in 100 year rainfall event. We can measure the consequence of that event by tallying up the impact that this event had on, say, the commuters unable to get to work, the loss of income from the commercial centers that had to close during this event, the cleanup, the repairs, maybe also too some downstream environmental costs, perhaps like through some sort of oil spill or something, that there is some unforeseen impact that occurs years later. The point being that consequence is quite a difficult thing to tally up and requires talking to many, many different stakeholders. But we can get some sense of what the consequence of this event is, and we can score it on our risk matrix here, along with likelihood. Now, we're lucky in this case, we actually have extreme rainfall climate data, historical extreme rainfall climate data, which not all locations have. But using this information, the fact that this is a fairly low likelihood event, 1 in 100 year event, and a fairly medium to high consequence, there was some flooding, there was some inconvenience, but it's not like the whole system was washed out completely, then our risk falls into that low category. So now you would want to take into account what climate change would mean for this system. We can do that in 2 ways. So first of all, let's imagine, well, and again, in this case, we're lucky. We actually have some climatological science that suggests to us that for places like Toronto, extreme rainfall events are expected to become more frequent and more intense in the future. This isn't the case for all places. And this is why it's really important to communicate and work with climate experts to try to find the information that's most relevant. And if you don't have that kind of information, to get expert opinion on what a suitable answer would be. But anyways, if we look at what a future 1 in 100 year event would be for this location, it's even more rainfall. And now we can do some further analysis of the consequence of this event and decide, well, actually, it's a much higher consequence. We're going to bump this into the medium risk category. And it would be the same, though, if we looked at that same rainfall event that occurred, which was a 1 in 100 year event, now shows up on the graph as a 1 in 25 year event. In other words, it's been made 4 times more likely to occur. That would bump us further along the likelihood scale into the medium risk category. So the end result, of course, is that climate change equals a change in risk. And that's what we're trying to drive home here. You have risk inherent with everything that you do in your engineering world. And now you need to take into account climate change into those decisions to determine if there's a significant increase in risk, and if therefore you need to design those systems differently. All right, what's the next slide there, Trevor? We've got, oh, right. You know, I think this is maybe a bit nicer way to visualize this. Let's just imagine here that we take some imaginary load on a system, like, for example, extreme rainfall, like we saw before, but it could be a high winds, it could be snowfall. If we plot load on this graph here, we'll see that we get some sort of bell-shaped curve where most of the time, the average of this curve is a certain load 2 on this graph. I mean, the units are not important. Rarely we'll have extreme values up near 4, potentially as high as 5 on this graph. Okay, so for engineers, when they're designing their systems, they probably produce a resistance to this load, and it would look something like this, where you've purposely over-engineered the system, perhaps to withstand an average load of 8. And on a bad day, maybe that load falls towards 6 and close to 5, but ideally, there is no overlap between these 2 curves. In other words, the resistance of the system is able to handle just about any load thrown at it. When we take climate change into account, what we're talking about is the shift in that load distribution. We have a shift in the average, but most importantly, the shift in the extremes. So now it's possible to have loads as high as 6. Importantly, because of this increase in load, our components are working harder. They're cycling on and off more, there's weathering issues, there's increased maintenance. And as a result, that resistance might actually decrease over time. That system will age faster than expected. Now we have an overlap between these 2 curves. That's the risk. That's the certain threshold value under which this load will exceed this component's resistance. And you could have disruption or a complete failure, or perhaps destruction of this system. Looking even further into time, what we tend to see with a lot of climate change variables like extreme rainfall, extreme temperatures, and wind, is that you don't just have a shift in the average, you have a shift in the variance of these distributions, where that curve actually becomes quite a bit flatter. And now, yeah, just give it one more advance. There we go. Yeah, so now that curve is much flatter than it was before. So the tail, the extremes go way further, you know, and here, if you look at the average shift, it's maybe just 1 or 2 degrees or 10 or 20 millimeters, but the changes in the extremes are much, much higher. And if we don't adapt our systems and that resistance continues to degrade, you have the potential for a lot more failure than you did before. Trevor, back to you. Any kind of comment on that though, before I pass it back over to you?
I think no, I think that was great. There's some comments in the chat on this. I'm sure we'll get into discussing this more in the Q&A at the end. Just want to use this reminder again. All we're really talking about is that taking future climate into account in engineering is necessary, possible, and both of the things right now. And so now I'm about to move into the both the possible and the right now by using some examples. David Lapp asked when setting this up if I could use some examples from BC that he and I were involved with. And in a couple of cases, I'm sure there's examples in Ontario, but I've been working in BC for quite a while, and they've been a little bit ahead of the curve on some of this stuff. And this example that I'm going to start with, this is a poster. There will be a link. This will be a hyperlink in the version that's shared, where we kind of told this story at a climate science meeting. I'm going to go through this quickly, following this timeline along at the front, but at the top. But I like this story because this story really starts in 1976, when a young Dirk Nyland, who is now, he ended up becoming the chief engineer for BC in the Ministry of Transportation and is now retired. But when he was involved in the original design of the Coquihalla, so this is the stretch of highway that failed last fall, and I'll get to that. When they were doing the design, they had 2 events in the same season that were rated as a 1 in 200 year event. And that just kind of made them go, what? And even in 1976, there was awareness of climate change. This is before we had any IPCC reports, but there was awareness of the science of climate change has been around for quite some time. And so, all they really did was double the culvert sizes, sort of an ad hoc response. But the seed of the idea of what ended up in the PIVC. And Ryan, actually, I'm glad you mentioned the acronym, because it gets at something that I'm going to try to hit on a few times, which is don't wait. It's the right now part of the third element of the slide we keep repeating. The word committee, I think, David Lapp can correct me if I'm wrong, but I think that's the very first hint that there's this idea that we need to think about climate change for a minute and then go back to doing the rest of our jobs the same as we did before. And so it was a committee, but here it is, this was early 2000s that PIVC was being talked about. We need more than a committee. It's really an ongoing process. And, it's sort of become an institution that's moved around from Engineers Canada and now has been sort of handed off to other stewards of the process. But it's become much more than a committee. So one of the first risk assessments, an early PIVC risk assessment, was done in the Coquihalla. It was done in the early 2000s. This is a real table from it. This is done using exactly that kind of consequence times likelihood kind of thinking that Ryan just walked you through with the Toronto example. And you had all the right people in the room so that you could talk about above ground infrastructure, below ground infrastructure, what would happen if we had this kind of event, and what would happen if we had that kind of event. And you can see a couple of reds, and you probably can't read the specific pieces of infrastructure, but it's really important that we actually, in this process, we go through very systematically. The PIVC process takes you very systematically through all of the bits of infrastructure, all of the different kinds of events. And actually this, that PIVC case study landed on a set of 14 high risks. They were all related to extreme precipitation and specifically atmospheric rivers. So this was in the early 2000s. We were aware of the risk. Several more case studies were done. A bunch of things were done that I think were kind of a consequence of being a bit of an early adopter in this area. So there was a state of the science on atmospheric rivers that was published, a climate language primer. That was, early on, we kind of, those of us who were trying to do adaptation early kind of realized that we were speaking completely different languages between engineers and climate scientists. Uncertainty to me just means a range of values. And I think to most engineers, when you hear uncertainty, you hear lack of confidence in the results. And it's not lack of confidence. We're very confident that the result is in this range. And so it's just a very different way of that can be important to take into account. Even the word mitigation in climate, mitigation is reducing greenhouse gas emissions, and in engineering, often mitigation is used to talk about exactly what we call adaptation. So getting on the same page about language is important. They even invested in improving the precipitation projections that were available. There was some comments in the chat about IDF curves, for example. At the time that these case studies were going on, we had very little information about daily precipitation. We did not have IDF curves at all. They're mostly started with just monthly projections. So winter precipitation or December, individual months may increase by 20%, 30%, and things like that. And there was very limited information about the sort of daily precipitation extremes. Okay, so a lot of stuff went on, and the main thrust of all of this, so it wasn't to go and make any adaptation to the projects that were being studied. It wasn't like the case studies that were studied. We didn't go back and replace any infrastructure. And I'll get into that again in a second. But the main thrust was to just get to the stage where we're requiring the use of future climate projections. And so BC has actually had that in place. That's part of one of the reasons for this example. I think they were the first kind of provincial jurisdiction in North America, provincial or state kind of jurisdiction, to have a requirement, a specific explicit requirement to take future climate into account. And it was through this 2015 technical circular. And they worked with the professional association in BC, started as APBC at the beginning, but engineers and geoscientists at BC. And I flipped between these two, not just for the name change, but to show that it actually took 4 years to go from, and it started with professional practice guidelines. And, again, it was a little bit ahead of the curve. That was a little too much for some members to take. And so it moved from professional practice guidelines more to just guidance that's useful to help people do this. And that's despite the fact that there was an explicit requirement in place coming from the Transportation Ministry. So all new builds that have been built in BC since 2015 have had climate. You've had to explain what future climate information did you use, how did it affect your design. But of course, that didn't help with the places that have already been built. So in this fall, we've all seen these pictures where we had a failure. And it was precisely the sorts of things that were the risks that were mentioned in the privacy report. In fairness, none of us had a crystal ball, and although these were the kinds of things that were mentioned, I'm not sure if we even knew for sure that this event would happen, how easy it would be to raise the funds required to have gone and replaced all of this infrastructure. It's pretty expensive it's one thing to take climate into account in all new infrastructure. Going back and, I'm sure you all know more well than I do how much of an infrastructure deficit we have. And we now have an adaptation deficit as well. This just kind of exacerbates that. So so just a bunch of images of all of the reports related to the knowledge that we knew about this, sort of 10 years ago. It's all sort of consistent with new sources of information on climate as well. But in terms of, so what did we learn from this? A couple of things. So the role of these kind of risk assessments is really important, especially to make the case for these explicit requirements on new builds. And I think we'll be I don't speak for Environment Canada or the federal government, the parts of the federal government that would potentially impose these kinds of new requirements, but just as a professional in this space, I think we will be seeing more and more explicit requirements from all levels of government. So the thing that we took away, though, is that if you look closely at those images, the bridges that failed, it was where the abutments met the road. I think that's the right word. And there was they were just not reinforced in the same way that bridges usually are in BC for a variety of reasons. And that's not something you could get at necessarily with a risk assessment. It's not something you can see by visual inspection. So to really get at this sort of adaptation deficit or adaptation pinch points is this kind of word that's getting used a little bit. This is, I think, where people are at, is that, okay, let's take advantage of these risk assessments that we do, not only to learn how to do them for new builds, but also if we're going to go ahead and do a risk assessment on old infrastructure, let's do a little bit more work and see if there are any really low-hanging fruit. Let's look at the biggest risks and see if there's some infrastructure that's particularly vulnerable to that, and see if it's actually worth some replacement. The other lesson, which I think is the theme of this, is that that timeline was very long. I mean, not counting the gap from 1976 to sort of 2005-ish. It took a long time to get to sort of where we are. And in the meantime, you can have a big event like we had in the fall here in BC. And so the longer we wait, the longer we're building in poorly designed, not things that are not designed for the climate they're going to experience. So the standard of practice can start to change right away, even if you don't have super explicit guidance on how to do on how to take climate into account. One more example from BC, and this one I'll kind of link to Ontario as well. So this is from buildings. There's a whole long story with buildings and hospitals trying to get climate taken into account in hospitals and things like that, which I'll save for the after chat time if people want to explore. But I wanted to make this point because I know a lot of you, have an interest in what we say is mitigation, the reducing greenhouse gas emissions side, the engineering solutions to reduce greenhouse gas emissions. And so it's important. I think buildings are a great example of where, even if your goal is reducing greenhouse gas emissions, if you use historical data only, you're sort of baking in some problems. And so here, this example is using energy modeling, some historical weather files, and then adjusting them for the future climate. If you take a building as it would be designed today, in the current standard of practice, it's evolving towards doing the right-hand side, but the current standard of practice using historical data only, this is what you design for a very energy efficient building. In BC, we have these steps, step 3, step 4 kind of building. But suffice to say, this is sort of partway between the requirements of the building code and like passive house. This is sort of LEED Gold or something like that. And so this is what you design, but that building already, and so what we're looking at is the number of overheating hours in the top floor, middle floor, and first floor. And so of course the worst unit is the top floor, southwest facing corner. And already today, this building designed using historical only data, already today that hottest unit is over the number of, so the recommended number of hours is to not be over is 200. You don't want to be over 200, which is about 2% of the time being over sort of human health guidelines. And by the middle of the century, the whole top floor is awash, and much of the rest of the building. So most of the building is well over human health guidelines. And of course, by the end of the century, under that worst case scenario, it's very far off. And the question is, well, how you design a building for this wide range of conditions, especially if you don't know which scenario we're going to follow. And I won't get into the details in the interest of time, but this just says, regardless of sort of where you're targeting, whether it's LEED Platinum or LEED Gold or whatever, what we're looking at now is kind of flipped things on the right. We're looking at that worst unit, that southwest top floor unit. This is the number of overheating hours. And this is by the end of the century. The full bar is by the end of the century, middle of the century, and this is already today. So again, these first 2 units already today are either at like over the minimum or pretty close to it. And one thing that this actually results from this is that the more energy efficient building is better today in terms, it's a little bit more adapted. And the other thing is that there are options. Again, I won't go through them, but you can do things with shading and window to wall ratios and stuff. There's stuff that you can do today that's going to be a lot cheaper. You wouldn't do it if you looked at historical data only. It wouldn't be worth it. It wouldn't have a good ROI, but it's way cheaper to do now than it is to go and retrofit later, because people are having human health problems the year after you install build the building, right? And just to kind of connect this to the rest of the country, this is from a similar kind of exercise. This is for reference medium office with cooling. Part of the issue you can see that kind of exacerbates this problem. I think it's even worse here than probably anywhere else in the country because we don't have mechanical cooling. So when you don't design, you sort of misdesign a building because it was cold enough in the past that you didn't need mechanical cooling, and now suddenly it's too hot for that. But even just to make the case, even somewhere like Toronto, even if you have mechanical cooling already, the cooling load for this reference building is, it's 30% increase or something like that. So even if it's there, it might not be able to handle the future load, and a corresponding over design on heating. That's kind of waste of resources. So just to wrap this all up for buildings, and this kind of touches a little bit on the sort of duty of care, but these quotes, we don't have a full EV exercise, but just think to yourself, if you want to read through these, I'll read through these quotes. Think to yourself what kind of document these quotes are from. I'll tell you what it's from in a second. So climate is not static. Past and ongoing greenhouse gas emissions are expected to alter most climatic regimes in the future. It can no longer be safely assumed that the climate of the last few decades will be a sufficient guide to the climate of the next few decades. Buildings will need to be designed, maintained, and operated to adequately withstand ever-changing climate loads. And now, usually, if I ask this, if we did do a poll, I think a lot of people would say IPCC, if you're familiar with those reports. You might say Canadian Centre for Climate Services. But in fact, these are from, so I first was exposed to the British Columbia Building Code. I believe these are inherited from the Canada Building Code. I've been doing a little homework to go further and further back. I first saw them in the 2012 BC Building Code, but I actually looked today and found that they were all of these words were already there as far back as the 2006 Building Code. So we know that climate is changing. You can't really claim that we don't know how to take future climate into account. We've known the risk is there. It's the how that is the hard part. And so we have a poll EV, and then a couple more slides and one more. So the question here is, did you have any aha moments or lessons learned, anything surprising in these buildings and highways examples? Sit on this for a second. Load versus resistance curve, great. Importance of reviewing after building, yeah. Thank you, never just rely on the past. That's what we're getting at. Much more expensive to react, for sure. More emphasis on cooling in buildings in the future. More buildings should look at heat pumps, yeah. Things that can deliver heating and cooling. Anything that gives you flexibility, gives you options, gives you resilience. Surprised by these quotes being in the 2006 BC code. Yeah, I'm curious how far back they go. I keep going one earlier and keep finding them. It changed a little bit between 2006 and 2012. We've known for quite some time what we used to do, yeah. Discomfort, financial pain, and distress, sorry. Preventing is cheaper for sure.
Nightmare fuel. Yeah.
All right, I'm going to keep this open. I've got just to make sure we don't go over time. And again, you will see all of the responses in the result that we send after the talk. Yeah, these are great answers. Keep them coming. Although do type quickly because we have only one slide and then another poll EV. So so I'm just going to walk through this real briefly just to give everyone who's currently typing on the last question time to finish. But just if you haven't noticed it by now, climate change, taking climate into account is messy. It's probably less, well, you can see this kind of schematic. This is less linear and systematic probably than you would like, but it's the reality. It's messy, and that's the reality of where we are. I mean, I liken it a little bit to, for any of you who are of a similar vintage as me, where when I was going to elementary and middle school, there was all this talk about seismic risk, and there was a long time where schools were being renovated to increase. This is a BC centric thing, but were being renovated to increase the seismic risk, and there was a good decade and a half where we had, from the scientific basis, we knew there was an increased risk of seismic hazards that hadn't been designed for. And it took, probably like it is with climate change, 10, 15 years to figure out how to really get to specific requirements. This is exactly how you do things, so kind of get to analogous to how the building code is now or other standards and codes. But there was this awkward time in the middle where new buildings needed to consider seismic risk, even though it wasn't exactly clear cut how to do it. And so we're sort of in that time, and we're kind of figuring out projects. You who are working in this time are helping to figure out the standards of practice for getting us to, defined guidelines and standards. And we're getting there more and more. But the main thing here is with climate change, we're going to have to plan for a wider range of conditions than ever before. And I'm going to go to the next slide. So there is one more question, and then kind of one more hammer this home kind of point. But so now what? Sorry, two more questions. This one more slide, and then one more question. What will be one challenge for you for taking climate into account in your work? Limited funding, for sure. I think we'll see a lot of that one said in a different way, convincing people to do it now. Like I said, I do recommend, we're not the ones to give this talk, but a talk on liability, standard of care. There's some folks who have thought through this a lot and give a good talk. It'd be great in this series, which RCPT is. We can help you with that. We've got resources to help you with that. Influence over decisions. If it doesn't make your clients money, it doesn't make us money, that's tough. So the building code, I should mention, by the way, so the latest building code, you'll see this in the resources. The most recent Canada building code does have, it's not part of the building code, but future climate projections were commissioned to go alongside to have exactly the same kind of variables in Appendix C, I think it is. What would the future projections be for all the Appendix C variables? And that actually does exist. It's in our list of resources. And as I say, I think it's ambitious, but there are a lot of people working hard to try to make it so that the next building code can have more explicit guidance on how to use that data as well. All right, so I'll leave that open. And like the last one, I've got kind of one more slide in between so you can finish typing what you were typing on that one. And then we'll end with the last question. So just kind of reinforcing a common theme throughout this talk and saying it in a different way. What we've been telling you is that with climate change, essentially you have a choice between being generally accurate or precisely wrong. And unfortunately, these are the only two choices. So, if I were to give you an option between, I can give you climate data for Timmins for you to design something in Toronto. I can give you the climate data in Timmins to 5 decimal points. Or I can give you the climate data in Toronto where you're building these days, but I have to round to only 2 significant digits instead of 5. You're probably going to want the climate data for the place you're building rather than for sort of the wrong place. And as a climate scientist, I really just view using historical data only when we know that climate is changing as identical to just designing for the wrong place. And so just to think of this in terms of generally accurate versus precisely wrong, one of the comments in the last slide was dealing with emission scenarios, which RCP do we use or which SSP do we use? You're going to get a sort of different number depending on which one you use. Which climate models do you use? Which variable? In some cases, you don't have, as I mentioned, you might not. Before we had IDF curves, we had to extrapolate from just the 1 in 100 year 1-year event and the 1 in 100 year 20-year event, and do the rest in your head if you care about IDF curves. We're now getting to the stage where there are IDF curves available, but there's method uncertainty. And so all of this keeps us away from the bullseye, but at least we're centered on the right thing. Whereas looking to the past gives us results that are much more precise, but they're not going to be the conditions we're to face. And all right, now moving into the very last slide before giving Ryan very little time to zoom through the resources. What is one step you will take in the next 2 weeks towards considering climate in your work? And Ryan, I think we're just a heads up, we're doing the short version, the 30 seconds each of the first 5 resources slides and then zooming through the rest. Trusting science is
Roger that.
That's great. Trying to understand what climate parameters must be considered into the project. Great. Considering going through some training, finding future data. And the slides that Ryan's about to walk us through will help you with that part. Supporting carbon neutrality, taking courses. I'm not sure what source control is. Maybe whoever wrote that can explain in the chat. Start the discussions. Yeah, just start. The more you talk about climate risk, the better. Great. Whoever considers it every day, that's great. Learning more, talking about it. All right, again, I will. Okay, cool. We have a keener. That's awesome. So I will leave this open. This is the last one, so you can take your time to answer this one. And yeah. I will go through this thing we've been hammering on. Taking future climate into account is necessary, possible, and Ryan's going to walk us through the things that can help you do it right now.
I have an overwhelming number of resource slides, and we knew we weren't going to get to them. So we are going to make this presentation available to you. This is like hopefully something in the past hour stuck, and now you need to do maybe a little bit more reading to solidify that learning. This is the reading. So the few slides here are, I think, the must reads, the things that you really should be aware of, and at the very least be reading the summary for policy makers section. So first of all, the CCCR 2022 report, which is the latest science and information on climate change in Canada, was dropped today. So it's a pretty great day. You can go to changingclimate.ca to read that. The biggest change is that there are new SSPs, they're called, shared socioeconomic pathways. So these are the scenarios that the climate models are running. They are new, they are refined, but they're basically the same as, and they map to the old ones if you were still using the old scenarios, the RCPs. So now, for example, we have SSP 1-2.6, which would have been RCP 2.6, and SSP 5 8.5, which would have been RCP 8.5. The key learning is that the science continues to evolve. The results that we've been seeing over the last many decades are still holding true, but this report's going to go through the very latest in science, so you can stay up to date on that information. Next up, we have a very important document put together by Engineers Canada. And all of these slides are linked to, yeah, exactly. The Climate Change Resilience for Buildings put together by RDH is a fantastic report. And we've been talking a lot about adaptation, but it's important to realize that buildings are an important component of mitigating climate change. So buildings, if they're designed properly, can reduce greenhouse gas emissions and so on. Yeah, thanks. Trevor's just pushing through these super fast because he knows we got to finish. You've seen this one listed already. This is the report Trevor highlighted from Engineers and Geoscientists, British Columbia. Definitely recommend taking a look at this guy here. We've got the high-level screening guide from PIVC, and in fact, it was mentioned in the chat. Sign up for the PIVC training, a fantastic training course, and the high-level screening guide is going to get you started on your process of doing your own impacts, vulnerability, and risk assessments. We've got webinars that you can check out that we've recorded here on the use of IDF curves and future IDF values. There's the latest information supporting through the Climate Resilient Buildings and Core Public Infrastructure project, where we have the new climate design values going into the next versions of the Highway and Bridge Building Code, the Building Code, and that sort of thing. there's this awesome video put together by one of our staff members, which is going to go into a lot more detail on the whole risk matrix process. And so this is a link to a YouTube video, so you can watch that. I prefer watching YouTube videos anyways than reading big documents. Really important resource is us, the Canadian Centre for Climate Services, and we have a support desk, which is pretty unique and it's pretty wonderful. You can actually reach out to us and get one-on-one support. If it's a simple question or you want to work with us through a larger project, give us an email, visit our website to learn more about that. We've got tons of resources, and yeah, Trevor, you can just start skipping through them here. We've got so many different data portals. The one I'm most excited about is climatedata.ca. It's got all these sector modules here, specifically the buildings and transportation ones. Various learning zone component here if you need to learn more, training materials. There's so much. And so we'll leave this with you to go through in your own time. So hopefully you can continue this learning process offline. So thanks so much. That was great. And thanks, Trevor, for going through those slides super fast.
Thanks, Ryan and Trevor, for your exciting presentation. I would like to come in to express our gratitude to all guest speakers and organizing committee members and volunteers. Thank you for your work, and maybe we could have some networking and additional question and answer session at the end of the seminar. So I'll pass my torch to Camille.
Great, thank you, Cristy. Thank you so much, Trevor and Ryan, for this amazing presentation tonight. It gives us a great perspective and understanding of available climate data and its limitations. And thank you for the list of must-read materials and videos. I now have homework to do after this session. Thank you both so much. I would also like to thank the event organizer, PEO West Toronto Chapter, and the co-sponsors for bringing this important topic to us tonight. Thank you so much. And finally, I would like to thank everyone for tuning in tonight and participated so passionately throughout the presentation. You've added so much fun and value to the session. Thank you, everyone. Now we'll have the East Central Region Councillor, Christopher, to give us the concluding remarks. Christopher, off to you.
Thank you, Kevin. And thank you, Trevor and Ryan, for a fantastic and interactive presentation. Well done, and we really appreciate your efforts today. And thank you, everyone, for tuning in today. Of course, today we've learned a lot about climate data, trends, and lessons learned that we surely benefit engineers across Ontario. But many of us in this meeting are employees, managers, business owners, and one common denominator that I saw throughout the presentation is that we can't manage what we don't track, and we can't track what we don't count. And data, and being data rich, is more important now than ever. We need to share that data with both engineers and non-engineers to help us make a real collective, informed decision, but also to make changes and positive disruption into our everyday routines. As seen today, the fate of the world depends on it. Just a little quick note, this all starts with recording data, crunching the trends, but very importantly, bringing definition to that data. What does it all mean? What do the numbers mean? And if you actually look back in history a little bit, before the fossil fuel era, engineers and inventors were telling themselves, in order to do something we never had, we must do something we've never done before, but the data wasn't there. Now we're in the fossil fuel era and we're trying to get out of it into the sustainability era. And as engineers and scientists, we're saying the same thing. In order to have something we never had, we must do something we've never done before. So I hope today, and I again thank today Trevor and Ryan for their insights. I hope it resonates with you as it did for me. And I want to thank them, Environment Climate Change Canada, and all the sponsors today. I'll now pass it on to my fellow PEO Regional Councillor, Jim Chisholm, for the final close.
Thanks a lot, Christopher. Before we actually get to myself, I'd like to introduce David Lapp, a retired engineer from Engineers Canada and author of several documents that come out of Engineers Canada dealing with climate change. David.
Yeah, thanks, Jim. And first of all, just thanks to Trevor and Ryan for fantastic presentations that really speak, I think, to engineers, and you've developed and refined this over many years, and will continue to do so. And you know, it certainly shows the importance of engaging engineers engaging with climate scientists to address these problems, and particularly, you know, getting the best data that we can, and to understand the limitations and the application of the data, you know, in the various ways that needs to be applied by engineers. You can see that it isn't just about you know, structural design of buildings or transportation, but you even get into internal systems to buildings, like as was pointed out, the mechanical engineers. So climate change really has an impact on virtually all disciplines of engineering in one way or another. So I really believe that all engineers need to have a basic awareness and competence to ask the right questions, and to really exercise, you know, part of this whole thing is about professional judgment. Yes, we have codes and standards, and those are improving and evolving as we get to know our climate better. But there is still the notion and the principle of practice that every situation is unique, and you don't just simply follow a code or a standard. You need to judge the situation as it is locally. And of course, climate data is an important component of that. But of course, you have to balance other things as well to come up with the best solution. And that requires engineering judgment. And so as regulators, we're trying to, as time goes on, and we started this at Engineers Canada to provide practice guidance at a sort of a national level, a consensus level among all of the regulators. And of course, as you saw, Engineers and Geoscientists BC is a group that, or is the regulator that is really most advanced in this in Canada. And so we're hoping as a PEO climate group to emulate that effort in Ontario, to bring climate change to the council, and to make it a priority within Professional Engineers Ontario. And it's been a journey, and it will continue to be a journey. But I think that if we have, as we go forward, practice guidance that speaks to Ontario engineers, we can, as the regulators, support and improve your competence to deal with climate change. And I would encourage, as was said a number of times, there's an incredible amount of resources, far more than there ever was when we first started this work, which is virtually, you know, in the mid 2000s, we started the PIVC work. But certainly, you know, we can see a tremendous amount of progress and momentum that will continue in the years ahead. So I think, you know, despite the doom and gloom of where climate may go, I think we have as engineers both a challenge and an opportunity on our hands here to affect more effective adaptation and resilience of our infrastructure and associated systems to our future climate. So I think there's lots of room for hope. And I would also just say as a last message, you know, to encourage our young engineers looking at their future career paths, that, you know, the whole area of climate change and engineering is ripe with opportunities, and there's lots of work to do. And I would encourage you to really, you know, pursue that path if it fits your passion, because I think it's there's lots of opportunities in the years ahead. So thanks for letting me speak, and appreciate again the presentation tonight. So thank you.
Thank you, David. And we're almost done, but very quickly, this seminar was organized by the Climate Change Group. David referred to it as an ad hoc group of mostly PEO members. Organizing seminars like this is one of the key things that it does. It also is working on encouraging the PEO to adopt the climate change issue into its 2023-25 strategic plan. And in addition, we're organizing for the AGM of the PEO, the annual general meeting, coming up in April. And David will be moving a motion that will ask the PEO to put the climate change issue very much on their agenda. I will be seconding the motion. We're just getting the final words worked out. Of course, David has to be comfortable with that. So if you're interested in participating in any of what I mentioned, do join our group, and you will have an opportunity in a survey that will go out at the end of this meeting to put your name down, and we can contact you and you can participate with us. And we do hope that we will have an impact in encouraging the PEO to make climate change an important part of their strategic plan. Okay, so that's the formal end of the meeting. So I'm going to formally adjourn the meeting. But as mentioned, if you'd like, stick around for a bit of informal networking. But at this point, the meeting is formally adjourned. Okay. Okay.
Okay, thank you very much, everyone. So I guess with this informal part, what we'll do is we'll get into some questions. So I know to start off, we had one from Martin, and I'm sure everyone's eager to know, how does Canada stack up against everywhere else in the world in terms of the climate science that you guys have been relating to, in terms of information? What's your opinion on this? Ryan and Trevor?
So the future projections that I showed, something that's kind of obscured there in the way I showed it. There's a range of values for each of the different scenarios. They actually come from a number of climate models, because there's about 20 some odd different climate modeling centers around the world, and one of the centers is here in Canada. Actually, it's in Victoria. Yeah, I think Canada has, I think, as is sometimes the case, outperform for our size, and our population. We've been a major contributor to the IPCC process and to the global climate model projections for decades. Each of these groups will have its own focus areas. One of the things that the Canadian Climate Modeling Centre has done, which has been really useful from our perspective as a climate service, is focus on large ensembles. And that is actually what, if you go to the CRB-CPI, the link that Ryan showed there to the climate resilient buildings and core public infrastructure, something that really enabled us to get these future projections of some of the variables that are in the building code are things that are tricky to get out of global climate models. And so I won't get into technical weeds, but because of the focus on large ensembles and in large regional climate modeling, which is at higher resolution, they're able to produce that report and it wouldn't have been possible otherwise. I'm not sure if that's answering all of the question. Just poke back if it's not. Also, by the way, I enabled the I don't think my screen's being shared anymore, but I enabled the we have the Q&A. I know you normally use Slido. Happy to just do quick Q&A informally, verbally or in the chat or whatever. But if you wanted to use that last poll Levy question, you can actually, doesn't work for those of you texting, but you can actually enter a question and you can vote up and down questions as well. So I think that one is active if anyone wants to use it.
Trevor, I'll add on top of what you said. We're pretty lucky that we have a Center for Climate Services. Obviously, that's the name of our organization. It's pretty new, and not many places in the world have a climate services center put together in such an official capacity. So we're pretty lucky. We're not top in the world. That I think probably falls to Copernicus there in Europe with the way they do their climate services, but we're doing pretty well. So it is. What is it? It's the small pond, and we have an opportunity, I think, to really outperform our population size, which is a lot of fun.
All right, and I'm also helping out with the networking part. So hello, everyone. Just want to remind everyone that feel free to use the raising hand function to ask any questions that you want to ask our speakers today live, where we welcome everybody. I know we have one. Sorry if I mispronounced your name. Preksha?
Yeah, that is correct.
Okay.
So thanks, Ryan and Trevor, for the presentation. I think that was very, very informative. The question that I have is, does the Climate Change Climate Services Center for Canada that we represent today, do they have a framework of advising various companies in different sectors or industries, say transportation or semiconductor industry, because we have a lot of fabs, on achieving the net neutrality target? Is there a framework that exists as of today that can be shared with companies in a specific industry?
So the short answer is no, because we're in the Canadian Centre for Climate Services. We're in the same branch, climate change branch, with folks who work on, Canada's net zero goals and that sort of thing. But there's just sort of separate lines of work. We are we're kind of grouped together with the adaptation policy group, because the climate services, our focus is really on providing the future climate projections, enabling people to use them. So our support desk would be able to answer questions about using the future climate projections. There are folks who can help you with the kind of question you asked. Ryan has been in federal government a little longer than me, and he might know who to point you at, but you can always email us and we can track down the right person to put you in touch with.
Thank you.
Yeah, I don't know off the top of my head, Trevor, the names, but yeah, absolutely. You know what I'll do is I'll just paste our email address into the chat. That'd be the absolute easiest way to get a hold of us.
Thank you very much for doing that. I'm sure a lot of people will take advantage of that. So the next question we have, is there any information on what homeowners can do to improve or update their house to help shield against increasing climate extremes? For example, wind, rain, cold, heat.
So the best resource for that would be the one by REH that Ryan mentioned. It might be a little bit BC centric, but it would be a good place to start. One of the author, or really the author of that, Robert LePage, might be in the audience, but he is now in Ontario, so he might be able to help, with converting that to maybe more Ontario relevant stuff. But again, our job is really, we're not housing experts. We want to set you up, those of you who are engineers who are involved with residential housing, for example, with this question, to be able to answer these questions.
Trevor, it's David Lapp here.
Yeah.
Just to help answer that question, another resource that has a number of I guess resources around that is called the Institute for Catastrophic Loss Reduction out of Toronto. And if you go to their website, iclr.org, there's a lot of materials around there and suggestions, pamphlets, etc., around climate, improving your home, because that's a focus. They're for the insurance industry, and so a lot of their focus has been on homes. So if anybody wants to look at some of the solutions that they offer, go to that website, and there's a multitude of resources there to give advice.
And while we're on buildings, there is one person who submitted a question to the kind of Q&A slide about if wet bulb temperatures would be one of those tricky variables. Yes, it is. Although there have been efforts to make the weather files, including wet bulb temperatures, so that are used in energy modeling, take future climate projections into account. The temperature I don't want to get too far into the technical details, but the temperature information is much more, it's at a higher spatial resolution, and there's sort of a lower range of projected future values in, relatively speaking, in temperature than in humidity. But the humidity aspect is taken into account in a slightly different way. So the main limitation there is that, so we haven't shown you any sort of spatial maps in this particular talk, but when you're able to find on some of the websites like climatedata.ca that Ryan mentioned, you're able to find temperature and precipitation projections there. They're at a pretty high resolution of about 6 by 10 kilometer grid. And that's for temperature and precipitation. We don't have that for humidity. And the main reason is because we don't have, the way we get to that high resolution is by creating a sort of statistical relationship between the global climate models, which are much coarser. They can't simulate the entire climate of the globe at such a fine resolution. We just don't have the computer power to do that. They've been getting finer and finer resolution, but they're on the order of 100 kilometers by 100 kilometers. And so for most places, that's just too coarse. It's like looking at a, pixelated image from early internet, right? It's just the pixels are pretty close. But that's kind of what we're limited to for humidity, because we just don't have the historical observations to create these statistical relationships with. We don't have high resolution observations of historical humidity. But there's some work going on that, but all of this stuff is always evolving. So at the moment, yeah.
There's one more question I think you'll answer better than me in the chat, which is the timeline for the new climate normals. Do you know when MSC will release those?
I don't know off the top of my head. I know that they're working on it now. There might be people in the chat who are following this more closely. I don't follow that super closely because when you're interested in the middle of the century, if you update the climate normals, then you also just need to need to update how you're referencing things, right? So yeah, so
I still like to use the 1990 reference period, as then I'll be able to sort of see how far we've come, so yeah.
Exactly.
But yeah, so sorry, I guess we can't answer that question fully, but it's being worked on, so.
Just wanted to remind the audience that we'll be ending this session at 8:40. So we'll try to get through all your questions, but we want to respect our speakers' times and everybody's time. So we'll have a hard cutoff at 8:40. So I see a hand, Nick.
Thanks. So I've been around this business for a long time, and I see building codes change very, very slowly. And although we're working with some progressive owners who are designing the future climate, like the BC government, most will just design to the building code, and it takes forever to change the building code. And it's still based on historical numbers. So we're building buildings now that aren't equipped for the future. Do you have any, Trevor, any insight into how we can get the building code changed faster?
So I think it's kind of two things. One is we have colleagues in Infrastructure Canada and NRC who are working very actively on these files. As we've made a big step forward in the last iteration of the building code, where we finally have future projections. I mean, if you go back all the way down to 2005, there's been acknowledgement of the fact that climate's changing. We now have the future projections to accompany it. They're not right in there, right in Independence, and there isn't clear guidance about how you use that. This stuff just takes time. I guess the only other thing that I would say, not as a federal government employee, but just as someone watching this and who's talked to a lot of engineers, there are engineers who have told me that they're just, they view their professional responsibility and their liability as, in jeopardy if they don't push back against some employers about this. I know that's hard. There are real cases. And like I said, I think that would make a really great topic for one of your future sessions. You can go through cases where municipalities or regional districts and the engineers of record have been sued successfully by people who, for events that happened, saying that they hadn't planned appropriately for it. And so that's, you know, you get into the difference between standard of care, duty of care, standard practice. There's a little bit of a mismatch between current standard of practice and perhaps a duty of care, and that can be awkward. I'm sorry, I can't.
And I think it's important to realize that building codes are not necessarily something to strive for, right? You know, and we can go much further with standards, and you know. And not, and I think, did I see someone? Yeah, there was someone even here who put this in the chat as well, right? Like, again, as a non-engineer individual, it's hard for me to know the correct language, but I've always been taught to say that building codes are, yeah, like a minimum standard anyway. So, and I think we, you know, our standards development are the like the SEC and the various standard developers out there like CSA are working, you know, on much shorter timescales to come up with, you know, design parameters that take into account climate information. Because yeah, it does take so long for these building codes to get updated sometimes.
Yeah, the problem is that they are the minimum, but for most, in most instances, they are also the maximum, and that's the issue.
Yeah, and I do think, I mean, I think it needs, you know, people were mentioning what will you do in the next week, and some of the examples, we'll just talk about it. And I think it's important at all levels. The housing and hospitals examples that I kind of alluded to and to get into, those were cases where, you know, the owner being a health authority who, and BC Housing is in a similar place, who, you know, they're kind of incentivized to care about the future occupants in a way that a lot of owners are not directly incentivized. And so they didn't want to build a hospital that's going to cause human health problems, or you know, or BC Housing that's going to cause occupants problems. So, and even in those cases, they found that procurement wasn't set up to be able to take future climate into account, even though the owner's asking for it, the engineers involved are asking for it, everybody wants to take future climate into account, and there's just a bunch of things in the way. And I think we could just have to push against all of that and keep bringing it up, that this is, you know, not taking future climate into account is as kind of incorrect, I guess you could say, as designing for the wrong place. No one would ever do that. You would never build in Toronto using conditions from Timmins. And so if you wouldn't do that, then why would you build anything that only looks historically?
All right, so I guess it's 8:40. I don't know, Cristy, if you want me to close this off, but just want to think from my part, I just want to thank everybody, and most importantly, our speakers. Thank you so much. That was very insightful, and we truly appreciate your time and effort in presenting everything to us. I'll leave it to Cristy for the last couple of words, and then we'll conclude this.
First of all, I would like to thank our speaker, Ryan and Trevor. You are really doing a great job and just so patient to answer so many questions. And I think our audiences still have several questions. You can find Trevor and Ryan's email in the chat, and you can follow up with those questions. And we have several resources to share on the PEO West Toronto Chapter's website. We'll be sharing the seminar recording there. Yes, so thank all the audiences, the committee members of this seminar, all the co-sponsors in Toronto and Ottawa and all across Ontario. Thank you for time tonight, and hopefully we can see you next month. So good night, everyone. Bye.
Thanks for having us.
Thanks, Trevor.
Bye-bye.
Thanks, Trevor and Ryan from David Lapp.
And especially thank for the West Toronto chapter who is leading this seminar. Louis is the head of the chapter. Louis, would you like to give some comments?
No, I'm not the head of the chapter, just coordinating the events of the chapter. Thank you very much, everyone, for coming today. I think that it was a great seminar. Thank you, Trevor and Ryan, for your time and for making aware all of us about climate change, the information about climate change. And thank you, everyone.
Bye-bye.
Bye.
Bye. Good night.
Bye, everyone. Thank you.